After studying this module, you shall be able to know the importance of Tanabe-Sugano diagrams, learn the interpretation of Tanabe-Sugano diagrams. You will also identify the parameters involved in the calculation of energy for the various transitions. You can analyze the various type of transitions feasible in the transition complexes. Also, you will learn the distortions which lead to changes in the absorption spectrum. Introduction. The Tanabe-Sugano diagrams are a special class of correlation diagrams in which the lowest energy free ion term is plotted as x-axis and all the other terms are hence plotted relative to this lower energy term. In these plots, energy of different groups of degenerate electronic states are plotted as a function of ligand field strength represented as delta naught. The parameter B is the Raka parameter, which is the repulsion term which arises due to repulsion between the terms of same symmetry. The ordinate is represented as E by B and abscissa is given as delta naught by B. The diagrams are qualitative as well as quantitative in nature. In cases where both high as well as low spin complexation is possible, that is D4, D5, D6 and D7 electronic configurations, a vertical line is drawn in the middle of the diagram to separate the high spin complexes from the low spin one.
We will start with the interpretation of the Tanabe-Sugano diagram for a D4 configuration. When we talk about a D4 configuration, both the low and high spin cases are possible in the presence of either weak as well as strong field, leading to the high spin or the low spin complexes. This possibility is further reflected in the Tanabe-Sugano diagrams in the form of discontinuity, which is quite apparent in them. Both the cases are represented in figure. High spin weak field D4 configuration has 4 unpaired electrons of parallel spin. In this case, the spin multiplicity comes out to be 5. In other case, the low spin strong field D4 configuration leads to 2 unpaired electrons with spin multiplicity of 3. The Tanabe-Sugano diagram of a D4 configuration is somewhat complex since now we have a vertical line in between that separates the weak field and strong field cases. On moving from the weak field to the strong field, ground state term also changes. The diagram for the D4 case is represented in figure, which shows the Tanabe-Sugano diagram along with the absorption spectrum for a D4 configuration. From the Tanabe-Sugano diagram, it can be observed that on the left of the vertical line is weak field up till the value of 27 for delta naught by B. The free ion term for a D4 configuration is 5D. In case of weak field, the term 5D splits with the ground state term as 5EG, having the anticipated spin multiplicity of 5. Now, as we move from weak towards the strong field limit, it can be seen that the ground state changes to triplet T1G, which actually correlates with the triplet H term in the free ion term case. The spin multiplicity of this term is 3, as was likely to be. Hence, the vertical line in between can be thought of as a divider which separates but relates the two types of fields, namely weak and strong. At the dividing line, the ground state changes from 5 EG to triplet T1G. Thus, the spin multiplicity also changes from 5 to 3, which suggests the change in the number of the electrons in both the electronic configurations. Above diagram also illustrates the absorption spectrum for the complex of the chromium 2+, which shows an absorption band at 14,100 centimeter inverse corresponding to 680 nanometer. Since water is a weak field ligand, it can be said that for this complex, left side of the Tanabe-Sugano diagram has to be considered. Thus, the origin of band can be said to be from a single spin allowed transition from 5 Eg to 5T2G. As can be seen in figure, this single transition band gives the energy of transition, which refers to the value of delta naught in this particular case. Hence, in order to find the value of splitting parameter, we simply have to find the energy of absorption for the corresponding transition band. Sometimes a single band in the case of few complexes of D4 configurations is split up into two due to the Jane-Taylor distortion. Next, we are going to consider a D5 configuration along with its Tanabe-Sugano diagram. In the case of D5 configuration, we can again have change in the filling up of electrons according to the weak and strong field. Along with the spin multiplicity also changes in both the cases. In case of weak field, there are total of 5 unpaired electrons and consequently spin multiplicity is 6. In case of strong field, there is only one unpaired electron which leads to spin multiplicity of 2. The Tanabe-Sugano diagram for a D5 case can be shown along with its absorption spectrum. From the Tanabe-Sugano diagram, it can be noted that free ion term 6s split up in the presence of ligand field having 6A1G term of the same spin multiplicity as the ground state. Now, in case of strong field, the ground state term changes to doublet T2G, which corresponds to 2I of the free ion terms. The vertical line separates the two states, namely high spin and low spin states. From the absorption spectrum of the manganese 2+ complex, some important observations can be made, namely the bands are very less in terms of intensity and the value of molar extinction coefficient. Also, the spectrum is very complicated due to a large number of overlapping bands. The reason for these two observations lies in the Tanabe-Sugano diagram for the complex. Before analysis of the diagram, some generalizations about the complex can be made. The complex here we are referring to is the manganese complex in the 2+ oxidation state with H2O as the weak field ligand, where Mn2+ ion is in the D5 configuration of the electrons with the H2O as the ligand, which is weak field ligand that certainly directs the formation of high spin complex. Now, if we are talking about a weak field ligand, we have to look at the left side of the Tanabe-Sugano diagram. By looking at the diagram, it can be noted that the ground state term is 6A1G. From this ground state, there can be no spin allowed transitions possible since there are no excited states of the same spin multiplicity. Hence, the bands observed are very less in intensity since originating from forbidden transitions. Due to this, the color of the complex is pale pink, which weakly absorbs, and thus low values of the absorption coefficient are observed. Also, since there are several excited states, hence several spin forbidden transitions are possible, leading to a complex overlapping spectrum. In case we are talking about the strong field ligands, there are again several transitions possible, but this time they are spin allowed. In this case, the Tanabe-Sugano diagram on the right hand side has to be considered, leading again to a complicated spectrum that is again difficult to interpret. In both the cases, determining the value of delta naught is quite difficult by the normal theoretical methods. Now we are going to discuss the D6 configuration. The D6 configuration is again having two sets of electronic filling depending upon the field applied. In case of weak field, there are 4 unpaired electrons leading to spin multiplicity of 5. When the field applied is strong, the number of unpaired electrons is 0, leading to a symmetric field with the spin multiplicity value of 1. The Tanabe-Sugano diagram and the absorption spectrum of the iron 2 plus complex is shown in the figure. The free ion term 5D dissociates in the presence of ligand field, where the ground state term is 5Du. In case of strong field, the ground state term changes to 1A1G, which correlates with the 1I term of the free ion states. In case of the iron 2 plus complex, the ligand is H2O, which is a weak field ligand. Thus, looking at the left part of the Tanabe-Sugano diagram, it can be noted that only a single spin allowed transition is possible from 5T2G to 5EG state. This transition is shown in the absorption spectrum of the complex, but looking closely at the spectrum, it can be noted that a single peak is split up into two. This is actually a result of Jane-Taylor distortion, which leads to splitting of the bands. The value of delta naught is given by the energy of this absorption band. Next, we are going to discuss a D7 configuration. For a D7 configuration, the weak field leads to the spin multiplicity of 4, and in the strong field, it alters to the value 2. The Tanabe-Sugano diagram of the complex along with the absorption spectrum is shown in figure. In this case, the free ion term of ground state is 4F, which splits into 3 states of same spin multiplicity, namely 4T1G, 4T2G, and 4A2G. The next higher term of same spin multiplicity is 4P, which transforms as 4A2G in the presence of weak ligand field. Under ordinary condition, the most populated state is the ground state 4T2GF. Excitation leads to 3 spin allowed absorption bands, namely mu1, mu2, and mu3, as given in the diagram. The transitions are as follows. Mu1 corresponds to 4T1GF to 4T2G. Mu2 corresponds to 4T1GF to 4T1GP. Mu3 corresponds to 4T1GF to 4A2G. The Tanabe-Sugano diagram for this case is quite similar to the D2 case, and the method to determine the value of delta naught is also same. Next, we are going to discuss a D8 configuration. For the D8 configuration, the electronic arrangement in the weak field as well as strong field is T2G6Eg2 as the ground electronic state. In the excited state, the electron from the lower T2G level is shifted to the Eg level. Thus now the configuration changes to T2G5Eg3. The ground state has F as the lowest energy term, which in the presence of the ligand field gets split up into A2G, T2G, and T1G. The difference between two lowest energy terms corresponds to the value of delta naught. Therefore, in order to find the value of delta naught, we simply have to determine the value of energy difference in between the two states A2G and T2G. The Tanabe-Sugano diagram for this configuration is represented in figure. Examples of this electronic configuration include nickel 2 plus complex with H2O as the weak field ligand. Next, we are going to discuss the D9 configuration. For a D9 electronic configuration, the number of electrons is 9, and this can also be interpreted as having one hole, and thus the Tanabe-Sugano diagram is quite simple to be drawn and to interpret. The configuration can be represented as T2G6 Eg3. Now, the excitation of electrons from the lower T2G level to the upper Eg level forms the excited state. The spin multiplicity of the ground and the excited state is same, and hence transition from the ground to excited state is spin allowed transition. The examples of the D9 configuration include the copper 2 plus complex having H2O as the weak field ligand. The Tanabe-Sugano diagram along with the absorption spectrum is represented in figure. From the figure, it can be seen that only one transition is possible from the ground doublet Eg state to the excited doublet T2G state. Thus, only one transition band should be observed corresponding to the value of delta naught. But in actual practice, a single absorption band is split up into two, as can be seen from the absorption spectrum. This actually occurs because of the Jahn-Taylor distortion, which leads to the splitting of the single band into two. Also, it can be seen that no Raka parameter is involved in the diagram, since only single excitation state is possible.
Summary. In case of D4, D5, D6 and D7 configurations, both the low and high spin cases are possible in the presence of weak field leading to high spin or strong field leading to low spin complexes. In cases where both high spin as well as low spin complexation is possible, a vertical line is drawn in the middle of the Tanabe-Sugano diagram in order to separate the high spin complexes from the low spin one. The free ion term for a D4 configuration is 5D. In case of weak field, 5D term splits into ground state term as 5 Eg having the anticipated spin multiplicity of 5. In the strong field limit, the ground state changes to triplet T1G, which actually correlates with triplet H term in the free ion term case. In case of D4 configuration, single transition band gives the energy of transition, which refers to the value of delta naught. From the absorption spectrum of the complex of the manganese, some important observation can be made, namely, the bands are very less in terms of intensity and value of the molar extinction coefficient. Second, the spectrum is complicated due to large number of overlapping bands. In case of the complex FeH2O6 2+, the ligand is water, which is a weak field ligand. Thus, looking at the left part of the Tanabe-Sugano diagram, it can be noted that only a single spin allowed transition is possible from 5 T2G to 5 Eg state. In D7 case, the free ion term of ground state is 4F, which is split into 3 states of same spin multiplicity, namely 4 T1G, 4 T2G and 4 A2G. The next higher term of same spin multiplicity is 4P, which transforms as 4 A2G in the presence of the weak ligand field. For D8 configuration, the electronic arrangement in the weak as well as strong field is T2G6 Eg2 as the ground electronic state. The ground state has F as the lowest energy term, which in the presence of ligand field gets split up into A2G, T2G and T1G. The difference between the two lowest energy terms corresponds to the value of delta naught. For the D9 electronic configuration, The number of electrons is 9, and this can also be interpreted as having one hole, and thus the Tanabe-Sugano diagram is quite simple to be drawn and to be interpreted. The configuration can be represented as T2G6Eg3. Only one transition is possible in D9 case from the ground doublet Eg to the excited doublet T2G state. Thus, only one transition band should be observed corresponding to the value of delta naught. But in actual practice, a single absorption band is split up into two, as can be seen from the absorption spectrum.